actually recording this time. Okay, so once again, I'm gonna briefly recap Ripley's K, and then we're going to move into Ripley's L. And just to remind you, so we're talking about neighborhood analyses, and the nice thing about these is these detect both regularity and clustering really well. And instead of using just the nearest distances like we were with D1, we're using all of the pairwise distances, which is a lot of distances. And we'll talk a little bit more about that in just a little bit. Well, you'll give graphic representation of just how many distances that can be. And essentially what we do then is we imagine a point process, like a distribution of points, with a density of lambda, which is our points per unit area, and then our K statistic for a distance of t is just 1 over that density times the number of events that you can expect within that distance t of some randomly chosen point in our point process. Now the cool thing about this is because we take that, essentially this is the density and then this is 1 over the density, it means that those things cancel out. This cancels out with this, hey, go back. No, you do what I tell you to do. And it just comes out to the area. So the expected value, what we expect to have for any distance or any value of t for Ripley's K, the expected is the area of the circle it inscribes for all densities. That's the expected. And then if we have a deviation from that, then we can tell it's clustered or random. So what we can do is to actually find our actual K statistic, what we do is we calculate the distances between all the observed, or all the pairs of points. We take all of those distances, which ends up being a lot. And then what we do is for increasing distances, we say how many of those points are within that distance, or how many of those pairwise distances are under a value t, which kind of gives you, if I choose a random point, what's the probability of finding one of those? And then we take that by 1 over the density, and that should come out to essentially just the area. Because again, this is an approximation. This number of points, point pairs with distances less than t, is essentially what we should get, or a surrogate for the area times the density. So if we take 1 over the density, we should just get the area back to this, if it's random. And so again, we're looking at give you an example of just this is our regular distribution that we talked about on Wednesday. They're all kind of nicely spaced out. There's none overtopping each other. There's been some sort of inhibition process. And this actually would get again, I should replot this. This blue dotted line that's really hard to see right here. On the top is our expected, so that is just as we go out 15, the area of a circle with radius 15 is going to be about 600 some odd, whatever pi r squared is of r of 15. And then our values are falling out below that, which we came to the conclusion that that makes sense, that it's actually, as you're more distributed, or as you're more regularly distributed, you're going to encounter new points at a slower rate than you otherwise normally would. Does that make sense to everyone? Does that intuitively not make sense? If it doesn't, I'll pause there and say that. You might not say it again, because I'll explain it another way. I'll just keep saying the same thing until you all understand me. You kind of have that voice too. We have a cluster distribution, and again here it's exactly the opposite. Essentially what we would find is if I chose a random spot here, what I would do is I'd probably find points more close to it than I would by random chance, because it's clustered up close. Which means as we go away from it, as we start moving away from our points, the number of points that we are encountering, we're encountering them faster at a higher rate than you would expect randomly. So those tend, again here, this blue line is our random, or our expected value for random, this blue line. And above that we have our K values. Again, this is the proportion of, essentially a area of the proportion of points that we're finding with distance from any given point, and that is higher than what we'd expect for random, so it can cluster. Yeah.
I'm a little confused still about
Okay.
how the k-value plot is found. Are you like sampling a whole bunch of random points for every radius?
No, okay, so essentially we're doing this. We are taking all of the pairwise distances. Okay? So, say I can do this really simply. So here, so that side wasn't because, like, this is a tedious question. That side was like, I'm thinking how to explain this, and my head is moving, like, in two different directions at once. So, I didn't want you to think, frickin' Spencer. Imagine this distance 1, this is distance, say, 10, and this is distance 11. So, that's not the way to do it. Click wrong. Essentially what our k value would be here is as you move out to 0.5, it's still at 0. As you move out to 1, it is this 1 times 1 over the density. Whatever the density it is here, it's 3 per, let's imagine it's actually just 10, like these are right on the line. So it's 3 over 10, so it's actually 10 over 3 would be 1 over the density. Does that make sense so far?
11.
Oh wait, 10 by 10 though. Well, 11 because it's like not straight above. It's like 10 straight up and down, so if you go this way, it's like 11. Anyways, but it's 10 by 10, so it's actually, we have an area of 100, we have 3 points in there, so it's 3 points per 100 square units, right? 1 over that then is going to be 100 over 3, or essentially 33, and then we multiply that by how much we have. So we have 1, so then our k value here would be 33. Does that make sense? Oh wait, this is 33, that's where we're at. However, at the same point, and then it would stay 33, so essentially it's here, and it's here until we get out to a distance of 10, in which case we have 2 points there, in which it goes up to, let's see, 2 times that, so we go up to 66. And on, and then it go up to that over here. Then it go up to 3 times that, so it go up to 100. Here at 11. And that's not exactly the scale. However, that being said, calculating our, yes?
So it only goes to, it's only capable of going 100%.
Yeah, because you don't have anything sampled outside of here.
The graph there is.
It only, okay, so this only goes to 100 because my total area is 100.
Oh.
Yeah. So it's not 100%. Is 100% the area? Yes, but I've also incidentally made the area of this 100. So that's a little bit. So the absolute area of the area that we sampled here is like 1500. Okay. Yeah.
So your algorithm that does this test will just go back through and redo this for every single point?
Yeah, well, essentially what it does, yeah, you have each point that you have, right? And as we add that on to the end, then we add 1 up. So we get a cumulative density function, essentially. Does that make sense?
Yeah.
Yeah. And then if we were to calculate this at 1, it's 1 squared times pi. So actually right here, we would be sitting at 3.14. Does that make sense why at 1 our r squared, yeah. Does that make sense why our, so we're above our distribution here?
Yeah.
Okay.
To make sure that I'm not, I might be like nitpicking this.
That's fine.
But it, like, as following along what I understood to be happening is, at the distance 1 from that first point we chose, it includes just that point. You increase the distance to 10, it includes that point.
Yeah, it includes a pairwise distance between this and this, and then this and this.
Okay.
Does that make sense?
And for a graph like this, you're simultaneously doing that, starting from the other points, or no?
Well, what you do is you get all the pairwise points, right?
Yeah.
All the distances, they're in one huge bag. So imagine that you just order all of those now, right? From the smallest distance to the biggest distance, right?
Oh.
Right?
Yeah.
And then you go, okay, to the first one, whatever that distance is, we jump up to 1. Over the second distance is, we jump up to 2, and we just keep doing that all the way. Does that make sense?
Yes.
Yes, okay. Very good.
So it doesn't even really matter where the points are, it just matters the distances between the points?
Yes. I mean, however, that being said, if you do this, pairwise distances, actually, there's usually only one arrangement that you can get for a whole bunch of pairwise distances. For instance, if I give you the pairwise distances for all of the cities in the United States, like let's say the most populous 200 cities in the United States, right? I give you all the pairwise distances. And essentially I give you like a multi-dimensional scaling plot, something that will solve for that, right? That'll say, okay, we're gonna arrange all of these so we maintain all those pairwise distances. Essentially it comes out exactly the same way that it would on a map. Because there's very few solutions for it. And it'll only come out that way, it'll come flipped upside down, it'll come reverse like this mirrored, or like upside down and mirrored, but there's a very limited arrangement that you can't. So like all the pairwise distances actually gives you tons of information kind of about the arrangement, because there's only so many arrangements that you can get with, like, for instance, if I have 100 points, that's a huge number of pairwise distances. I can't even, there's a way to come up with that, and I'm not gonna do it in my head. So, does that make sense?
Yeah.
Okay.
Yeah. When you say pairwise distances, like this would just be a vector, like for this case of 1, 10, and 11.
Yes.
Okay.
Yeah. And so with 3 points, there's only 3 pairwise distances. Yeah. Does that make sense?
Yeah.
Okay.
It's remarkable that you could like reconstruct a map from just that.
Yeah, I should show you guys sometime. Yeah, it's actually kind of crazy. And actually, usually it's a table, because then you have this point, and you have the distance, this point, distance. So it's like a distance table.
Okay.
But it's also, you can take that and just string it out. Like if you didn't even have the labels, you can also
Still works with
yeah. So yeah, you have this, and then this would come out very clustered, because these 2 points, in all of this, for those 2 points to come out only one distance apart when there's 100 square units here, that's relatively clustered. So in this case, this comes out above our expected. It's 33, the expected is 3, so we're like 10 times as high as our expected K value at that point. So saying, hey, at this radius, we have a lot of clustering. Now, all that being said, you can get different, this is a very, like, just doing it this way, generally algorithms are gonna add on edge effects. Because again, these are on edges and this is on edge right here, we're actually gonna get a skewed estimation of KT because of these edges. And so, like, oftentimes it's applied to toroidal, or something else like that, like an edge correction. And so, is this making sense so far?
Yes.
Yes? Good. Okay. I want to make sure this is making sense, because then we're going to go on to something that is derived from this, which is the L-stat. L-stat, not L-stat. No one's going to lie here, right? Anyone? Maybe not. Okay, anyways, so again, remember then our simplified KT then is just this. Which means then we can kind of modify this and try to solve this for 0. So then take this and divide pi or KT by pi, and then take the square root of it, and then take all of that minus the distance, and that equals 0. And what this means now is that if we calculate a statistic this way, the KT divided by pi, take the square root of that and minus t from that, the expected now for the L stat, or the L statistic, is 0 at all distances. Which makes this a little bit more easy to interpret, because it's easy just to interpret random data should be 0 for every distance. If we have a deviation from 0, then that is what is interesting. Now this is a little bit more interesting because if I go back to this, what is random right here? I'd have to like crank through some numbers and figure that out. However, if I have an LSAT, it'd be, oh, well, 0 is what random data should be. And so it's really easy to see deviations from that. It's easier to understand. There's a little bit more work to calculate through, but not too awfully bad. And if you stick an R, it's relatively easy. Okay, so for this, it actually comes out different because we've shoved everything on the other side of the equation. This changes our sign of things. And so negative values for L is clustering. So if it goes below 0, this is indicative of clustering. If it goes above 0, this is indicative of regularity. However, this is a common way to calculate L, but for whatever reason, L just kind of like arose naturally because it's better than K. But also means that people calculate differently depending on what you're doing. So some people actually calculated that it's just this, the square root of, they don't take the minus t out of here, which means that L is the distance. So it's a 1-to-1 relationship. So at distance 1, the expected is 1. At distance 10, the expected is 10, and so on like that. It's a linear relationship. That's a little bit less easy to visualize, but if you're reading a publication that is using the L statistic, check it before you check which way they're doing it, and they will usually say what version they're using. Okay, so let's look at what this looks like in real life again. This is our regular data. And so what would you expect the L statistic to do with this over distances represent here? Would you expect it to be positive or negative? What's that? Positive. And here the actual L statistic for this value. So, hey, it does go positive. It's positive at all distances, but it's very positive here at moderate distances, right here. Very positive. Okay, so you might be saying to yourself, maybe you are, maybe you aren't, I don't know. Maybe you're saying to yourself, okay, so that's great, so it's positive, but is it significantly positive? I mean, anything is going to be nothing's going to be exactly 0. You will never get anything exactly 0. So is this different than what we could expect in the distribution of a just randomness? So how do we test for that? No, go back. Okay. How do we test for that? And it turns out, hey, randomization comes back because there's no simple parametric way to test this, especially when we're testing values at a whole range of distances. So something could be significant in one region, but not significant elsewhere. So for instance here, what we do is simply we make a bunch of random point distributions. We essentially go back and we generate our plot like this, but we just start throwing out random points. And we do it for the same density. So we are going to essentially keep the same sampling area, keep the same number of points, but just randomly throw them out there. And then calculate the L statistic again. And this is how we do it with the K statistic as well. And then we get, for each value, we get what is the variation that we can see in this K statistic for each value as we move out. And what happens is we can either take a 95% confidence interval. We usually do that if we do really, really large number of randomizations, say more than 100. Or if we do 100 or less, we usually take the minimum or maximum. And it really depends on how big your data set is. If your data set is really, really big, and it's going to take a lot of time to crunch through the numbers, people tend to do fewer randomizations because just computer time. And then what they do after that is just take the minimum or the maximum of that. If they have smaller data sets that run relatively fast on this, they will tend to run more and more randomizations, say like 1,000 or 10,000, then take a 95% confidence interval. So this is what that would look like. Okay, so we have our L statistic here, and then we can usually add in lines that show the bounds, and this is just for 100 randomizations. I took the minimum and maximum. And for random data, this is what I found. This is the upper limit of what random data gave me with 100 randomizations. This is the lower limit, and this is the mean. And you notice the mean is falling right about 0, a little bit of a dance in there somewhere, but right around that. Here's min and max. So anything where my actual test statistic is outside this envelope, it is significantly different than random data would produce. And so this is kind of nice, because now what I can see is between about 0 and up to about 5 meter or 5 units distance, whatever that is. This is very regular distribution. They are closer than what you would expect. Or no, they're more distant from each other than you would expect. They tend to be not clumped, more regularly spaced. However, as we get beyond that point, as we get beyond about 5 units, the existence of one unit essentially has no impact on where another one exists, which is kind of what we would expect. Because if we're regularly spacing each other, imagine if we were to all get up and kind of like space each other out randomly, I'm going to have a very strong effect on where my immediate neighbors are. They're going to kind of space themselves out from me. But someone on the complete other side of the classroom doesn't really care where I'm at. They care where their immediate neighbors are at. So you have very regular distribution with accordance to your immediate neighbors, but you have very little regularity in terms of who's on the other side. Does that make sense? Okay. And that's essentially what this is reflecting. We have a very regular distribution. The regularity is at about a spatial scale of about 5 units. We come back in here. For instance, this point, or let's say this point, it has a lot of influence on where this point is at and where this point can be. They couldn't be closer, but this point and this point, there's very little influence of one over the other. Are there any questions on point pattern analysis at all? Yes?
Where does your p-value come from? How do you get that?
Okay, so you actually don't get a p-value for this.
Oh.
Because you would have like thousands of p-values.
Yeah.
Because essentially, for a similar thing, you would have a p-value for every point along here.
Mm-hmm.
So essentially, we just demonstrate graphically where we have, okay, if we're outside this, we are at a significant p-value, and we say p-value, so to speak.
Yeah.
And if we're inside, we're not. Yeah.
Oh, wait, no, that makes
Okay.
sense.
So.
Is there any like value to or way to report like the magnitude of difference across that range? You know, like just find the area. Is anyone interested in that kind of thing?
I guess you could. I have not seen anyone do that. Yeah. Because here's another thing. Even if it barely comes out and comes right back in, you're not going to get much for an area. In fact, if you try to compare that to everything else out here and try to get one aggregate p-value, you will probably not get much of anything.
Yeah.
Because it's aggregating. But it's still interesting. Because still, at that point, with hundreds or thousands of randomizations, you still can achieve at that one distance the kind of point pattern that you see. So it's still interesting. But if we made one aggregate statistic for the entire thing, it would be completely washed out. And it's a little bit different, because this is, normally you would think, well, multiple comparisons, and it's going to screw up our, but that's not really the case here, because they're not all independent. Does that make sense? So if it's all kind of independent analyses, and we're kind of looking at the all, yeah, multiple comparisons would be a problem, but these aren't. Any other questions? All good questions. Okay. With that, I will move on to my next lecture, which is kriging, which is fun. And for this moment, there's a lot of weeds that I'm not going to get into. I'm going to try to keep it very surface level, so give you the things that you need to do kriging. There is a lot under the surface of kriging and a lot more math here, which honestly is not necessarily the point of this class. I'm trying to get you very applied, so I'm going to do my best to keep it less math. Oh yeah, hey, remember to start the video, because this was supposed to be the beginning of the class right here. Okay, so there's a lot of different things that we can measure in space, and we've just been talking about measuring positions, x and y. Or even we can do point pattern analysis on x, y, z essentially the same way. Get pairwise distances compared to a random distribution. Great. Or importantly, hypothetically, we could do the point pattern analysis in any number of dimensions that you wanted to. We could do it in 3 dimensions. We could do it in 6 dimensions, which would be really, I don't even know how to visualize that in my head. It makes me want to take a nap. Actually, I think 8:30 in the morning is what makes me want to take a nap, but we'll pause there. Oftentimes, however, at these same positions, we have other data. Like, we get position data, and we don't, like, it's not just a position, we have other data associated with that. Like, hey, we went to this place, and it has this XY coordinate on some area, and we also got, like, a temperature there. Or we got the depth of the ocean there, or we got the amount of carbon in the soil there, or we got some other measurement that was associated with that point. Those are very useful. However, when we do this, oftentimes we simply cannot get values for every single place that we want. We do not have an actual measurement of that, whatever that value is, somewhere that we want or everywhere that we want. And if it varies spatially, we have a problem. We have to figure out what that is. So for instance, imagine I wanted to go to my house and figure out what the temperature, I didn't measure the temperature at my house, but I wanted to get a good guess of what the temperature was at my house. I could get the closest station. I could say, well, it's basically that. Actually, with temperature, that'd be pretty good, but imagine a world where temperature varied, like if you walked across town, the temperature would be fairly significantly different. That'd be funny, that'd be weird. I kind of like that. I'd like to be able to figure out where the coldest place in town is and go there all the time because it's getting way too hot. It's getting so hot that I was openly wondering if I should start wearing a kilt yesterday. What's that? Oh no, I just heard something.
Oh, there's a brand called Untitled.
I have seen that, and I love their little YouTube commercials.
Yeah.
I know. I totally thought about I started wondering how much this costs because.
They're very expensive.
Are they really?
I mean, I think anything above $50 is really expensive. So
Okay.
I don't know, we're probably on the same.
It's more than pants.
Have you seen the oatmeal on utility kilts?
No, I have not. I need to.
It's totally inappropriate.
Is it? Okay, I need to go watch that. The oatmeal on utility kilts. Okay, well, I've been openly wondering if I need. Yeah, it's getting too hot. Let's just leave it at that. I'm not going to go any further with that one right now. Anyhow, so imagine a world in which you could travel across town and hey, the temperature would drop 5 degrees. Actually, if you look, there's actually a handful of weather stations across town. Imagine if I didn't know what it was in my house, the temperature of my house, and I wanted to interpolate what it was. I would need some method of doing that. And if looking at the nearest value is not sufficient, then we need something more. And that's where our hero comes in, named kriging. Which almost sounds like a name to me, or like you're doing something in someone's name, like, I am kriging. I am Kurting. I am Spencering. I am Matting. Wait, Matting might be. Anyways, what kriging is a method of interpolating values in space. If we have a bunch of spatial data and we know values at that space, we can interpret those. And we do this based on the weighted distances to other known values, or we're weighting the values based on the distance. So for instance, as things are closer to you, we weight them in the interpolation higher than things that are further away from you, which kind of makes sense. Things that are closer to you should be more predictive of what your value is, if there is spatial correlation. And this includes estimating the spatial variance. This is important in doing this. So for instance, we need to know what variation can we expect with a certain amount of distance. And we do this by constructing something called a Semi Variogram. I'll talk more about that in a moment. So, let's imagine, and this is kind of the point pattern that I am going to be using for this. Imagine each of these dots is a value for something. I think actually this is well depth in some area, with bigger circles being greater well depth to actually get to water, and smaller circles being less well depth. Yeah. So you notice a couple things first off. Number one, it varies spatially. We have places with high well depth. We have very deep well depth. Yeah, high well would be weird. We're pumping out the clouds. And then down here we have very shallow wells, and that's grand. I say things sometimes. I just and do things. Anyhow, so and here's another thing I want you to notice about this point pattern is that areas that are more close to each other are more similar to each other than places that are not close to each other. So if I pick two random points, like here and here, they're more likely to be different than here and here. And that's what is known as spatial correlation. To interpolate values like this, there needs to be spatial correlation. If there's not spatial correlation, there's no data there that we can interpolate from. Like imagine for a minute, I took you and just scattered you around the room and then measured your heights. There would be probably no spatial correlation. I doubt that people that are taller will aggregate together with each other and people that are short. Maybe they would, I don't know. That might happen. But in general, it probably wouldn't. So I couldn't estimate someone's height based on the people around them. However, there's a lot of things that are spatially correlated, like this. Basically because there's an aquifer below here that is at varying depths, and it actually controls how deep these wells have to be. And imagine a world in which I want to drill a well right here, and I want to know, well, is that going to take more materials than when I drilled a well right there? And I know you're all going into the well drilling business, so I figured this was really important to tell you about. So again, let's talk about the assumptions that need to be fitted or need to be met for us to go through kriging. And the first one I just talked about, spatial correlation. We need to have points that are more similar to ones close to them than you would expect from random points. The next thing is we need to have this thing called first order stationarity. And what first order stationarity is that there's not a trend surface. For instance, if I go west, wells just keep getting deeper and deeper and deeper, and that just continues forever. It needs to have no general trend surface. We also need to have what's called second order stationarity, or that the variance is uniform throughout the study region. We can't have the variance changing dramatically between one end to the other end. We can't have like really high variance over here and then really low variance in this other point, because we're going to essentially be applying the same model over the entire region, and so the variance has to be relatively even. Now, this is generally the case, but you need to check that, and we'll talk about how to check that. And then you also have to have this thing called, I'm just going to say it the way I don't like, isotropy.
What's the way you do like isotropy?
Yes, isotropy. Which it follows the, yeah. And I've only heard a few people say it that way, but it sounds so much better, isotropy, rather than isotropy. Anyways, you need to have isotropy. I don't say this word enough. I should start just dropping in normal conversation. Anyways, and what this means is that the variance between points is only dependent on the distance between those points, not the direction. So the variance between two different points, so the amount of randomness between them should go up as we get farther away, and that should be essentially equivalent to whatever direction away from you I go. If the randomness or the unpredictability increases one direction as opposed to another direction, we're going to have a small problem. And we need to correct for that. And essentially all you do is, there's corrections, essentially if you violate any of these, there are corrections for that. You don't have to worry so much about it. And then the final thing that you need is normality of the data. The data has to be normally distributed. And we're talking not about in space, like the actual spatial area of it, but the values that we're looking at have to be normally distributed. Okay, so let's talk about the steps that we go through to actually perform kriging. And the first thing that we do is that we have to test our, yes?
On the previous slide, what's the difference between first order stationarity and isotropy?
Okay, so isotropy, well, first off, this one is the actual values. This one is the variance between values, first off. Number two, isotropy can be symmetric. Like, east-west can have decreasing variance, where north-south, so it can be symmetric and you don't have a trend surface. Whereas this can't be symmetric. You are increasing in one direction. If you increase similarly in all directions, like you're really low here and then you get just wider every direction that you go, it's not a trend surface. Does that make sense? Yes. Okay. So those are two things. Good question though. Okay, so in kriging, we have to first, the steps in actually accomplishing this, number one, we have to test our assumptions. So we go through and we actually test that all is it true. If we fail one of those assumptions, then we have to go back and do some sort of correction or use a different kind of kriging. The next thing that we have to do is we have to fit what's called a Semi Variogram. I'm going to talk more about this in just a few minutes, but we fit this to get 3 different values, which are called the sill, the range, and the nugget, which I think is one of the cooler terms in all of statistics, the nugget. It actually was called the nugget because when this, I think I'm remembering this right, when this was first being applied, it was being applied to trying to find ores in the ground. And the nugget would be essentially, we found a nugget here, and we found a nugget here, and then it kind of worked its way into there. So I think it actually, most of this has come out of geology, the methods here. So, okay.
Literal makes it even more amusing.
I know. This is, never mind, I'm going to bring that up. Okay, anyways, and then the final step is to do the kriging, which is kind of nice. And we're going to use the sill, the range, and the nugget, plus the distances to other points, and the values of those points to interpolate unknown points, which is kind of fun. Okay, so let's go through each of these steps and start talking about what we do. First off, we have to test these assumptions. I'm not going to talk about this right now too often much because I'm going to save this for lab. I mean, you run through a handful of tests. You guys probably basically know how to test for normality, and you do that. And then you test for an isotropy, which then you do that. And isotropy is just the opposite of isotropy. Yeah, so we do that. The next thing that we do is then we make the Semi Variogram and extract those 3 values from it. So a Semi Variogram, is just plotting a plot of the semi-variance between points by the distance between them. The semi-variance being 1/2 of the variance. And if there is spatial correlation, no! Samsung has a mind of its own. Actually, I keep pressing it against myself, and it slides. Anyways, if there's spatial correlation between points, we should expect, as those points are closer to each other, as there's less distance between them, there should be less variance, right? Because they should be more similar. And if that's not the case, we have failed our assumption of spatial correlation. So as you move closer, you should have lower and lower variance. But they should only go out to a certain point. Like, for instance, if I was looking at soil carbon in the middle of centennial grain, if I go like 2 steps away, it should be somewhat related. If I go 2 steps away, it should be somewhat less related, but still related. If I go 5 steps away, it should be somewhat less related. If I go to Idaho, it will not be related at all, because Idaho is just weird. And then if I go all the way to Maine, it should still not be related at all, which means then that the variance between soil carbon in some random place in Idaho and random place in Maine should essentially be the same, because they're not related at all. Does that make sense? And so at some point you should reach a level at which the variance does not keep increasing, because it's just, there's no relationship. The variance is just whatever the variance can be in that measure. Does that make sense? Okay. So let's take a look at how this looks. Here is that distribution of wells with our individual things again, and what we have is then paired points, and then we can get from each of these. I'm not going to talk about how we calculate the semi-variance. Just know that lower semi-variance means that they're more similar to each other than higher semi-variance. So we're going to look pairwise between each of these. So for instance, I'm going to take this point, I'm going to get its pairwise distance to every single other point in here, and then get the variance between this and that point for every single one in there. And keep doing that for every single pair of points we can get. And if we plot the variance by the distance, we get something that looks like this. Lots and lots and lots of points, but here's the cool thing, it goes down as you approach 0, and then it tends to go up, and that's just the rest of the way. Just a big, horrible monster. And you look at that and you look at that, that's really noisy and disgusting, and I don't like that. And you're right, it is. So normally what we do is we need to simplify this down somehow, and we do that by binning our data. We say, okay, we're just going to take sections of this, and we're going to take an average for every single point in that section. Average for every single point in that section, average for every single point in that section, all the way down. And what we do then is we get bin this Semi Variogram, which looks a little bit something like this, which is a lot more reasonable to interpret. So, and what you can see here is kind of exactly what you would expect for something that's spatially correlated. It's low as the distance approaches 0, but after that it tends to get increase and increase to a point where it gets just high and it just stays flat. Okay, so from this Semi Variogram, we need to get out these 3 different things: the nugget, the sill, and the range. And this is they. So the nugget is the variance or the semi-variance at point 0. Essentially, the nugget is the intrinsic variation in this measure. If I took the same measurement, the same place, or very close to the same place, what kind of variation could I just expect at that one place? And sometimes this is 0, or very close to 0. Like if I took the air temperature in one place right here, and I took it right here, it's going to be very close to 0. They should be essentially exactly the same. Sometimes it's kind of high, like if I was looking at soil pH, and I go here and here, well actually with very short areas you can get pretty different results, and so on. And then that increases to some point where it becomes flat. That maximum variation is known as a sill. This is essentially the maximal variation that you can get from between any 2 random points in that area. And then the place at which our model reaches the sill is the range. Now the range is really important because the range sets the upper limit of where another point has any predictive value for a given random point. This is the furthest point in which we have correlation, spatial correlation between our point of interest and another point out there. Beyond that, it does not help us to use these points to help interpolate a point. But inside that range, it's still useful. We can still actually look at it and it makes sense to use that data to help us interpolate a point inside that range. So are there any questions with that so far? Okay. There's actually a whole bunch of different models that we can use to do this, but I think I'm going to leave that. We only have 2 minutes. But when we come back on Monday, we're going to continue with Friday! Not Monday, Friday! Boy, that voice came out of me. I interpret that as being Scrooge when he first sees the ghost of Bob Cratchit. I I don't know why that popped into my head. I know I have Christmas stories like percolating around in my head at this moment. Mom, Cratchit! Anyways, when we come back on Friday, we're going to talk more about that. Actually, we're going to talk more about this in lab because we're going to do a bit of this in lab. We're going to talk about different points, power analysis, and do all that fun stuff. And I will see you in lab. We will this week meet down in the ecology lab, not here. So meet us down there. So with that, enjoy your day. I'm actually kind of disturbed that I record all my lectures sometimes. It makes me wonder constantly if I should be doing that or that. I mean, is that just sealing my